Okay, let's start. So, firstly, any questions? Homework, design assignment, anything? Okay, wanted to spend a little bit of time on describing the design assignment. Some of you I know have already been asking questions about it and all. So, this basically requires you to do a couple of combinational designs using Logisim. Um, the first one is basically a system where you take a code which is 5 bits, but it's supposed to represent either a 1 or a 0. So kind of the idea is the following, that oftentimes in communication systems, we need to send bits. The problem that happens is that because of noise in the channel, those bits get corrupted. So we need to code them somehow so that there is some resilience to those errors. And one simple scheme you might imagine is the following, that when I send the bits, let's say whenever it's a 0, instead of that I'm going to send 5 zeros. And whenever it's a 1, I'm going to send 5 ones. And then on the decoder side, the idea is that if I'm going to look at the group of 5, and if majority are 0, I'm going to declare it to be a 0. If majority are 1, then I'm going to declare it a 1. Another way of saying is that I can have up to a couple of bits of error, and I'm still going to be able to recover it fine. So basically, you're going to tolerate some degree of error. So what this first task asks you to do is to design the decoder side. The transmit side is very simple. Okay, it's a decoding side that we are interested in. So you're getting a group of 5 bits, which is represented as, which in case of our system is a DN, which zero is a 5-bit signal. And basically, if majority is a 0, then majority of the 5 bits are zeros. Then you are going to make D out to be 0. If majority is 1, you're going to make D out to be 1. So it's a 5-bit combination of logic. The constraint here is that I want you to design it using only the basic gates. So you're not allowed to use multiplexer or decoder or those kind of things where, as we have seen, we can very easily implement combinational logic. So I want you to go through the exercise of designing these things, something like this from scratch. There are many different ways you can approach this thing, Karnaugh maps, or just staring at the logic, or using the analysis capabilities within Logisim. All of those things are fair game. The way we are going to grade it is we are going to, so I'm trying a sort of a new grading system here using GradeScope. So basically what I do is I've uploaded a auto grading script to GradeScope, and it's going to basically run your design on a bunch of tests. This is a simple enough thing, there are only 5 bits, so I can do it exhaustively. And the deal here is the following. If we are going to compare against my design, which is hopefully correct, well, it is correct. Each error, each mismatch is going to cost you 25% of the points. It basically means that once you hit 4 errors, you have a 0 score. Okay, so you should test it exhaustively as well, basically. Okay, so that's the first one. Second one is more complicated, somewhat. So in this case, I have 3 4-bit numbers, A, B, and C. These are the inputs. And there is a 4-bit output, which is called median. And you might recall last lecture I was talking to you about how can you find the median and stuff like that. Okay, so this problem is basically that. How will you find the median? So your output should be the median of the 3 values. The 3 4-bit numbers, you have to interpret them as unsigned binary numbers. So like 0110 is the number 6, and so on and so forth. So you just 1111 is the number 15. So you have to find the median. On this problem, you are allowed to use any of the gates that Logisim has. Okay, so now one thing to be careful is the following, that the modules which are in Logisim, they are different, like even the ones which are named the same, multiplexer or decoder, they have some extra pins, they behave somewhat differently than the one I described in the class. You are responsible for consulting the library reference manual. So in particular, neither the TA nor I will answer any question for which we know that you could have just looked up into the reference manual, because I want you to go through that exercise. Oftentimes in future, when you are faced with design, you'll basically have documentation and you have to consult documentation to extract the relevant information. That's part of the homework. So please do not use us as a shortcut to reading those things. You have to go through that exercise yourself. But you're allowed to use any of the modules that are available in Logisim. So I think I say that much out here. Now, here again, one of you had pointed out the discrepancy between 8 bits and 4 bits and all, and the reason was I first had it as 8 bit, and then I tried the autograder and it was taking ages, so I reduced it down to 4 bits. So again, we'll do an exhaustive test, except that in this case it is 12 bits, 12 bits of input, so that's a fair amount, but for the autograder it's easy. For you to manually do it, there are a couple of ways you can do it. One is you can think about whether using any of the Logisim capabilities, you can do exhaustive testing. In particular, Logisim has a concept of test vectors. So you can try that out, read up on that, see how you can use it. Okay, just like you test software or testing hardware. There are other ways potentially to also do it, so I'll leave that up to you. Or alternatively, you think about what the cases are. So in this case, we are asking you for the median. Median is the middle number. So you can try out different orderings. You can look at special cases like, what if 2 of them are the same? What if all 3 are the same? Are you behaving correctly? Is the system behaving correctly in those cases? So you narrow your test space. Again, I want you to go through that exercise to kind of see how you test a design like that. Much like you would have done for software. You wrote a piece of code for median. How do you know it works correctly? So you, again, go through that kind of exercise. So that's one thing. Another aspect is, just like when you write software, you're usually given the spec. Your function should take these arguments, your function should output this value, all those sort of constraints. In hardware, we similarly have constraints that you have to sort of comply with. In this particular case, because of Logisim, the way it works and the way, therefore, we autograde, there's an additional constraint also, which is, so besides the pins having the right name and all, there's also a constraint that those pins must appear at certain specific relative positions in the design themselves. So in previous years, I used to give out a spec that this pin should be at the top and this should be at the bottom, and almost always some students would not read it. So this time around, what I've done is I have given you a file in which I've already positioned the pins, and I have put prominent comments in the homework. Do not move them around. Okay. So I want to show you what that looks like, and so there's a file which is called da1.circ. You're going to download that, and basically you are just going to modify that file. Keep saving the file periodically. Make backup copies of it. I have had 1 or 2 instances where someone's computer crashed in the middle or whatever, crashed the file. That's, sorry to say, your problem, but I can only advise you, so keep saving. Okay. So you're going to fire Logisim. So the typical command I use is, I'm calling the circuit here test.circ, and I'm firing it with the analyze option, which, as I've shown in one of the prior lectures, makes visible capabilities about truth table and those kind of aspects. Okay, so I'm opening it up with that, and okay, so what you would see out here are 3 subcircuits. Now, 3 circuits. So Logisim a Logisim file can have multiple circuits in them. And the idea is I can use one circuit as a sub-circuit in another. So you can think of these circuits as like functions, and I can instantiate or call a circuit from another circuit. Of course, I cannot have loops. I cannot have like A calling B, B calling A. So it has to be a tree. But I could do that. So in this case, I've already pre-populated 3 designs. So one is this DA1_1, the very first one. That corresponds to task number 1. And let me blow it up. So you see I already have 2 pins out here, D in, D out. They're currently unconnected. There is no logic in between. But I could, let's say trivially speaking, for example, I would say, hey, I'm always going to output a 0. Okay, so in that case, I could do the following. I could use the constant, wire it up, change the constant value to 0. In this case, I have a design which, irrespective of the input, is outputting a 0. Of course, it's a wrong design, but I just want to make a point. Let's say you decided now I want to do something else. Maybe I want to OR all these 5 bits, and whatever is the result of ORing them is what I'm going to output. Again, wrong design, but I just wanted to make the point. So what I will do, for example, is I'm going to split. So here I have a 5-bit signal. So to OR them, I have to split them into 5 separate bits. So I could go to the wiring, and there's a splitter out there. I would encourage you to read upon it, but so let me do the following. I'm going to show you some another thing also. So the splitter currently has 2 bits coming in, but I want to have 5 bits coming in. And I want 5 individual bits going out. So what has happened now is the stem side is the one where the bundle of bits come in. Okay, and that is affected by the bit width in. So I set it to 5 because I have 5 out here. And then I separate them into 5 individual bits. And then I'm going to OR them together. So let's get a OR gate. Again, bear in mind that this is a wrong design, but just wanted to show you. So I make a 5 input OR gate. I wire them up. Okay, I can remove this stuff, these text items. I can connect them like this, and I can okay, and you can check whether it works correctly or not. So if I make one of them a 1, the output changes to 1. Okay, so it works correctly. So in this case, my algorithm was, hey, I'm going to OR the 5 bits. Of course, again, incorrect algorithm, you have to work it out. So you could wire up like this for simple design. This is fine. I want to show you a couple of additional capabilities on what you can do. So sometimes all this excessive wiring can get cluttered. So another thing we can do is make use of a feature in Logisim called tunneling. So let's say I don't want to really kind of wire this thing up out there and wire this thing up out here. I want to have a cleaner design. Okay. So you would see under the wiring part of Logisim something called a tunnel. And the idea behind tunnel is it's as if I can magically connect 2 parts of a wire, but not actually draw the wire between them. So I want to connect this guy to D out. So I make 2 copies of the tunnel. Think of it like a wormhole. Okay, so I'm going to creating that. Okay, I want to set its orientation right. I'm going to put this guy close to this guy. I'm going to give this tunnel a name. So let's say I call this guy net2, and I'm going to call this guy also net2. And what this says is that these 2 are connected. There is a wire there between them. This often is useful to avoid clutter in the design. In the simple example, it's obviously pointless, but And likewise, I can do the same thing out here. So I can create another tunnel, attach it here. And now this tunnel, you see it gives me an error because it's not the right number of bits. So I need to change the number of bits to 5. So that tunnel becomes okay. Let's give it the name net1. And I put another tunnel out here. I change its orientation. And again, change the number of bits to 5. Oops. And give it the name net2. Oh, net1, sorry. Okay, so this way I can have more complicated design at different parts of the drawing canvas and not have to draw wires all over. So splitters, these tunnels, these are useful things. Then oftentimes, even with all of this, the design is way too complicated. So then what you can do is you can create sub-circuits. Okay, so let me show how that can be done. Well, I can demonstrate this thing right with this only. So see how I have a design on this circuit is DA1_1. It has an input pin called DIN, output pin called DOUT. Let's say I want to use it somewhere. So I'm going to create a new circuit. Let's call it test. So you see how a new circuit called test created out here. I'm going to go to its canvas, but now I'm going to instantiate a copy of what I had previously created in that other circuit. So now I have a symbol corresponding to DA1, DA1_1, which is out here, and you see how it has a D in and a D out. Okay. So your task for task 1 is to flesh this guy out. I've put some bogus stuff out here, but you will be putting some circuit which is going to do that. Majority is 0, then its output is 0, majority is 1, output is 1. And I leave it up to you how to design it. Like I said, you can do hand analysis, you can use the, since we called this thing with the analyze option, there is a analyze circuit option, so you can use that, but be very careful. Analyze circuit option overwrites whatever is in the canvas, so you might want to do it on a blank canvas, get the circuit there, copy it back out here, cut and paste. So you can use that, but you have to stick to basic gates. DA1_2 has likewise the pinout for the second task located. So it had 3 4-bit numbers coming in. So those are the ABC and 1 going out. Let's say, again, I want to do a stupid design. So I say, hey, the median is always B. Okay, I can output that. Of course, you are going to get wrong a very large number of times. So this is a sure way of getting a 0. So you have to figure out what to do. In this case, you can make use of anything. What I would suggest is first think about how do you find a median. Let's say you were writing a piece of C code or Java code, you were given 3 numbers, how would you find the median? And then think about how you can instantiate it in the hardware. Last time when I was talking about multiplexers and all, we had seen some examples how we could do max and stuff like that. Very briefly speaking, multiplexers are how you, in a sense, end up creating if-else kind of structures. And then we had things like comparators available which can let you compare things. So you have the basic goodies of this. Okay. You'll probably be using the comparator here because we want to compare numbers. One thing to notice that the comparator in Logisim, so if we go to arithmetic and we see a comparator, so let's say I instantiate this comparator out here. What you see is that it gives you a number of bits, but it also have numeric type. By default, it uses numeric type 2's complement, which we are going to see in today's lecture, but 2's complement is for representing signed numbers. In this problem, we have unsigned numbers. So you're going to change this thing if you decide to use a comparator to unsigned so that you get the right thing. So make sure to change those values. How to access the manuals and all, those of you haven't figured out, under the help, there is user's guide and library reference. So let's say I go to library reference. It opens it up. I go under arithmetic. Go to comparator. It describes that. So all of that stuff is there. Under you might want to read this test vector setup on how you can use feed large number of input patterns and examine its output. It also has logging capabilities and it logs the outputs. So there are many different ways you can test this. Of course, you can always test by clicking the pins to change their values. Okay, but and then just do them selectively. So again, you have to work out kind of the strategy. You don't need to submit any of your paperwork. We just need the design. We will check the design both for testing this thing and whether you are obeying the constraints, as in whether you are using anything other than the allowed set of gates. Okay, and we are going to check for whatever potential cheating. So that's the third test that we run. Those are things to sort of go after. Any questions? Yeah, in that case. Okay. But I would be able to tell whether it's a logistic generated design. Yeah. By the way, just to let you know, you won't be able to run the truth table on median, it's just way too big. Logistic truth table only works up to 5 bits, so, or I think actually 4 bits, so you probably may not even be able to use it even for the first design without doing some decomposition. Yeah. You had a question? Okay. Any other question? One thing, couple of things. Please do not create any other circ file. Your file has to be called da1.crc. Okay. Do not move those pins. Do not add any pin. Do not relabel the pin. Do not move them in any shape and form. Okay. Very important, because in Logisim, unfortunately, the way that software works is these pin positions matter. And if our autograder if you change them, then what may happen is autograder will just see X values, and of course, then it will grade it as not meeting the test. So, and so this is why I'm providing you these things, so that minimize the chance that you're going to mess with anything. Feel free to create additional subcircuits and instantiate them the way I kind of just showed. So, complicated part of the design, you can put them into a subcircuit. All of those things are fine. Keep saving again and again. And then in the folder itself, make a copy, okay, like literally copy it into some other place of your hard drive, okay. When it comes time for submission, you're just going to upload it, just like you did with the current assignment, except that this time around there is nothing about showing which page it is. It's a programming assignment, is a separate concept and grade scope. So you're going to upload it, and at some stage we are going to run the test script, and you get the score. So that's kind of a basic structure out here. Again, all the information in the manual is out there. The kind of questions we will answer are something which are not clear in the manual, as opposed to using us as a manual lookup thing. So there are no shortcuts. I want you to go to that. So if no questions, I'm going to move on to the main lecture. None? Okay. Giving you a peek into the path ahead, we will have, I'll also be sending out a problem set this week. So there are a total of 4 problem sets over the course. So we'll have basically 2 on this material and then another 2 kind of soon after the midterm. And then we have 3 mandatory design assignments, and the 4th one has that optional flavor to it, where you can choose to do it or have more weight to your final. So just want to remind you of that. Okay, so let's get out of this and switch to the main lecture. Okay, so last time around we had started on this module, so kind of the idea is now that we are moving into dealing with numerical values, and I guess until now we had basically been, whenever it came to numbers, we have been interpreting bits to represent unsigned numbers. They are like whole numbers, so 0, 0, 0, 0 is all 0, and then 1, and so on and so forth. I had shown that how we can think of them in terms of weights. So rightmost bit has a weight of 0, so a weight of 1. Next bit is a weight of 2, 4, 8, powers of 2. They go like that. And therefore, given a particular bit pattern, you can get its value by essentially multiplying each bit by the weight at that position, then summing them up. So in this particular case, if I have a 5-bit number 11001, I add them up, you are going to get the number 25. So its value is 25. And given any 5-bit pattern, I can think of it this way. Now, of course, just positive integers or 0, 1, 2, 3, those are insufficient for doing a lot of science and engineering and other things. So we need other kind of numbers. We need negative numbers, we need real numbers, we need all those kind of things. So then the issue becomes, how do we represent those? We saw earlier in the course that bits are just bits. We can interpret them whichever way. We can interpret them as cards in a deck, colors on a wheel, numbers, whatnot. If I say that I have a k-bit thing, then what I have to play with is 2 to the power k patterns. I have a set of 2 to the power k patterns, and then I interpret them whichever way I want. When we say that these numbers represent binary integers, then we are choosing to interpret them a particular way. We are saying that if you give me a 5-bit number, then it corresponds to the value which is calculated by multiplying the bits by the corresponding weight. And the weights are given in that particular order, 1, 2, 4, 8, so on and so forth. But that's a choice we made. It has nice mathematical properties, but there's nothing sacrosanct about it. We could have done, for example, other way around. We could have said the weight of leftmost bit is 1, and they go as 1, 2, 4, 8 rightwards. That would be perfectly fine. Maybe in cultures where you write from right to left, like Arabic and all, maybe, I don't know, but perhaps they represent numbers that way. But most languages and all, we kind of go right is least significant and left is most significant. Actually, does anyone know Arabic? Do the numbers also go the other way? No. No? Okay. Okay, so I guess the numbers there also are the same way. Okay, so so bits are bits. That's the point I want to make. If I have a bunch of bits, then I have a bunch of patterns to play with, and it's really up to us to assign a meaning to them. Hardware doesn't care. Hardware sees bits, it sees gates. The gates operate a particular way. It's the meaning we assign to them which then connects it to some application. And so it really sort of, the whole thing boils down to what meaning do we assign if we are interested in representing something. And like I said earlier in the course, we saw how to represent things like dates and cards in a deck and those kind of things. Or in the problem set, you saw how to represent colors on that color wheel. So the question really out here is, how do we represent, what constitutes a good way of representing signed numbers? What constitutes a good way of representing real numbers? And remember, if I give you a set of bits, it's certainly fine if the hardware at one moment thinks of it as a signed number, and at a later instant thinks of it as a unsigned number, or maybe thinks of it as a real number. All of those things are fine. In software, this is often done. Those of you who program in C, I have a variable, I can cast it. I can cast a variable into a different, I can take the address of a variable to get a pointer and then cast it into a totally different data type. That's all okay. Deep down, it's a bunch of bits. So all of that is up to us. So now let's talk about some kind of games that we can play. So one problem which often occurs is, so given a binary pattern, we know very well how to get to the value. But let's say I give you the value of a number in decimal. So like if we had given you that 25, or in this example, I gave you 17. So I've given you the number 17 in base 10. That's a little subscript. And I say, hey, what's the binary representation of this, assuming in a conventional manner, okay, where weights go as 1, 2, 4, 8 from the right. So what we can do is we can start with the number 17. I can divide it by 8. That basically tells me, I divide it by 2. I get the number 8 and I get a remainder 1. So that basically tells me whether this number was odd or even, or actually it's really telling me the least significant bit. So it's basically saying my number is 2 times 8 plus 1. So that 1 goes to the least significant bit. I now focus on the 8 part. It's basically saying I have 8 tools. Okay, so I play the same game again. I divide 8 by 2. I get 4 and a remainder of 0. So this remainder goes into the second least bit. So number basically becomes 1, 0. So I'm sort of going from the right, play the same game. I have 4 divided by 2, again a remainder of 0, and then 2 divided by 2, 0, 1. So this is my number. So sort of I start getting bits on the right hand side. How many 1s, how many 2s, how many 4s, how many 8, you can work backwards from that. So this could be done relatively easily. You could even imagine, for example, so the way I have described is how if I were to ask you to write a piece of software where took a number and printed out the binary representation, you could implement it like this. Now think about what if I were to give you the number as this decimal number as bits. So for example, this 17, I can say, hey, what if I were to create a box which takes 2 digits, digit digit 1 and digit 0, and these are the digits themselves can be representing 4 bits, so they are 4-bit numbers. So in my case 17, so 7 is going to be fed out here, which would be same as 0, 1, 1, 1, and 1 is going to be fed out here, which is 0, 0, 0, 1. So I can represent this decimal number 17 as 2 groups of 4 bits corresponding to the 2 digits. So now I have an 8-bit pattern coming in, and I feed it into this box, and I want the output to be, so since I'm feeding it 2 digits, so my maximum number is 99. So how many bits do I need? 7 bits, right? 2 to the power 7 is 128, 2 to the power 6 is 64, so I'll need 7 bits. So you could imagine implementing this algorithm as form of a box like this, which takes 8 bits, output 7 bits. It's not trivial, so I'm not going to go through it, but conceptually at least you could kind of do it. Now the problem with this algorithm that I showed is it has a step sequence. It needs to remember what came in the previous step. So this algorithm that I showed is a sequential algorithm, right? I do things step by step. I remember what happened in the previous step. In particular, I have to remember the quotient from the previous step. So in this case, it takes 5 steps. More generally, it would take 7 steps because I have 7 output bits. But I could also create a combinational logic for it. So I can convert decimal to binary and in this particular way. Binary to decimal, we already saw that's easier in a way because we just have to add things up with the right power. Okay, so I can go back and forth. Binary numbers, if we were to tend to be very verbose because everything is just in terms of zeros and ones. So essentially, every digit becomes a little bit more than 3 bits. So that can be very painful. So for compactness sake, usually these numbers are often represented in hexadecimal form. And the idea in hexadecimal is that we make groups of 4. So remember, hexadecimal is base 16. Base 16 means that I'm going from 0 to 15, so I'm basically using a 4 bits. So this number that you see out here, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, this actually has a value 1963. I can multiply this thing out with the appropriate weights, goes all the way to 12th bit, but I'll get 1963. But this is writing 12 characters. So 2 verbose. So what is done is to compact it out by taking groups of 4 starting from the right hand side and then assigning them to the corresponding base 16 digit. So 1011 is the value 11, and since in base 16 our digits have to, after 9 they go as A, B, C, D, E, F. So this is the digit B in hex. Likewise 1010, which is a numeric value 10, is a hex digit A, and 0111 is the hex digit 7. So this number can be written as 7AB, and this is equivalent to saying what did I do? Okay, this is equivalent to saying 7 times 16 to the power 2 plus A times 16 to the power 1 plus B times 16 to the power 0. And A has a value 10 and B has a value 11. So it is really 17 times 256 plus 10 times 16 plus 11 times 1. And you add them up, you are going to get 1963. So that those groups, since they accumulate, they correspond to 4 bits, the weight we give to them are now in terms of 16. So you can easily go back and forth between the two. Going from binary to hex means groups of 4. Going from hex to binary means just replacing them by the corresponding bit patterns. Okay. So now we can go from decimal to binary, binary to hex, and back. All for still positive numbers. Positive integers, 0, 1, 2, 3 onwards. So now let's look about how we can add numbers. So, and we are still in this realm of binary numbers. So let's say I have these 1-bit numbers. So adding 1-bit numbers is easy. 0 plus 0, their values are 0, so it will be 0. 0 plus 1 is 1, 1 plus 0 is 1. 1 plus 1 is kind of interesting because 1 plus 1 is the number 2, the number with value 2. I cannot represent it in 1 bit. I need 2 bits. So it would now become 1, 0. So that's what we see out here. In general, if I add n bit number and a k bit number, how many bits do I need? So 2 numbers, one is n bit, another is k bit. In general, how many bits I need for the output to represent the sum? N plus k. Okay. Not really.
That's the maximum k and n plus 1.
Yeah, maximum of the 2 plus 1. So if you think about it, right? I mean, let's take digits. Okay, if I had 5-digit number and a 3-digit number, then at most I can have the 6-digit number. If I have 2 5-digit numbers, at most I can have a 6-digit number. So it's the maximum of the 2, but 1 added to it. Okay? So now multiple bits. So in normal decimal arithmetic, we start from the right and we have a carryover, right? We add digits and we have a carry. And that if I'm adding 2 digits, then I can have a carry of 0 or a carry of 1. 9 plus 9 is the worst case, 18, so 8 and a 1 carryover. In this case, in case of binary, it's the same thing. 1 plus 1 is 0 and a carryover of 1. So same logic applies out here. So I have two numbers, 6 and 3. In decimal is 9. In case of binary, they are 110 and 011. So I'm going to add them together. So I add the 0 and 1 at the LSB. I get a 1 with a carry of 0. So now I add 3 digits, 0, 1, and 1. If I add 3 bits, the maximum I can get, again, is a 2-bit number, right? Because worst case would be 1 plus 1 plus 1, which is 3, which is representable as 1, 1. So it's 1 and a carry of 1. So this is fine. In this case, 0 plus 1 plus 1 is, what do you think would come out here? So I'm adding the carry of 0, and then already I had a 1 and a 1. So what would I get there? 0, right? So I get a 0 out here and a carry of 1. And then now I have 1 plus 1 plus 0 is the same story, 0 and a carry of 1, except that now I'm out of bits. So this goes down there. So my number is 1, 0, 0, 1. Okay. Okay. So that's the binary addition. We can try other examples like this. Okay. So now sometimes we are faced with a situation that I'm restricted that my output has the same number of bits as the input. This happens in software. Like you are running on a 32-bit computer, your integers are 32-bit. And when you add two 32-bit numbers, you still are storing it in integer, you're still storing it in a 32-bit number. Or in my example out here, maybe I have a computer with 3-bit numbers. So 3-bit, 3-bit, output is 3-bit. Well, now I have a problem. When I add, I may not be able to store it in 3 bits. And that condition is called overflow. Okay? So this indicates I have an overflow. And whether there is an overflow or not depends upon the specific numbers. So if the numbers are small enough, then they will not result in overflow. How do you think I can figure out whether there is overflow or not? So I give you, let's say, I'm creating a 3-bit adder, two 3-bit numbers going in, a 3-bit number coming out, and I want you to give me a signal saying whether an overflow happened.
Your result is smaller.
Okay, result is smaller. That's a great insight. So smaller than what?
Then both numbers put in.
Both numbers you fed in. It would be. That is true. Okay. Another way is to look at whether I have a carry out. The carry out is acting as my. So his interpretation we'll see later as to why that happens. But in this example, I mean, whenever the carry out is 1, carry out of the final bit is 1, that means I have an overflow. So if I design a circuit like this where I have carry outs happening anyway, then carry out tells me what's happening. Now let's look at what circuit do we need to make this magic happen. So firstly, one thing you realize is at every bit position we are doing the same thing. We are taking the 2 bits I have and a carry which is coming in, and I'm producing the bit for the sum at that location, and I'm producing a carry out. So essentially I have to create a circuit which takes AI, BI, which are the 2 bits of the operands, an output bit, it takes the carry, actually what have I written out here? Let me just make sure. Yeah, okay. This one actually doesn't. So for now, at the least significant bit position, let's just go back. So let's first focus on what happens out here. In this case, there is no carry coming in, or another way of saying is I have a carry coming in of 0. So because I'm at the least significant bit, so I have to add 2 bits. So my circuit would, these are my inputs, and I need 2 bits of outputs. These are my outputs. And this column is just indicating the numerical value. So if I have 0, 0, I need an output value 0, which really corresponds to some bit of 0 and a carry out of 0. 0, 1 becomes sum of 1, carry output 0, 1, 0 results in the same thing, and 1, 1 represents this. So I basically have a simple combinational circuit which has 2 bits of inputs and 2 bits of output, a sum bit and a carry bit. Let's focus on sum bit. This is a sum bit. Can someone tell, and these are my inputs, right? A and B. Can someone tell me what gate it is? No, it's not OR. XOR. It's an XOR. Okay. What about the carry? It's an AND, right? So this seems simple enough circuit, and it's called a half adder. It's called a half adder because it's missing the carry coming in. It's just focused on. But this is what it is. Okay. Now let's look at the higher bit positions. Higher bit positions also have a carry coming in. So they have 3 bits of inputs. They have carry in and the A and the B. And now again they have to produce 2 bits of output. So this is how they look like. We can work through this. So for example, let's look at this row. A carry in is 0, A is 1, B is 1. So I have 0 plus 1 plus 1, that's 2. And therefore I have a sum bit of 0 and a carry out of 1. So that's what we are seeing out here. 1, 0. Let's take this guy. All of them are 1. 1 plus 1 plus 1 is 3. That corresponds to 1, 1. So sum is 1, carry is 1. So for every all possible 8 combinations, I can work this thing out. So I'm essentially doing now adding 3 bits. Okay. So one way I can think about this thing is this whole thing is again a combinational circuit, one with 3 inputs and 2 outputs. I can implement it, and it's called a full adder. Or if you think about it, we are really adding 3 bits. So we can think about adding 2 bits and then adding a 3rd bit. So I could use half adder to make up a full adder. I could approach this problem in multiple ways. So if you look at this thing, the sum bit actually turns out to be XOR of 3. It's a 3 input XOR. And if you look at the carry out, it's a majority circuit. It's saying if the majority of the 3 input bits are 1, then the carry out is 1. So it's a majority circuit. So it's drawn out here. And now how would I make my n-bit adder? I'm going to take a half adder for the least bit position, and then I'll have a bunch of full adders, and I'll feed the carry out of one stage to the carry in of the next stage. So I'll have a long chain. We have seen circuits like these before when we discussed comparator and arbiter. Same thing. There's a long, it's a bit slice design. Carry ripples through from bit 0, bit 1 all the way through. And again, as we saw in those designs, the delay here will be proportional to number of bits. So this kind of an adder takes, as the number of bits increase, there is a linear increase in the delay of the adder. Now, I could implement it in terms of gates. We have seen this majority circuit back several times. And I could also actually implement this thing, this circuit using 2 half adders. Conceptually, half adder adds 2 bits. I have 3 bits. So I can add them, I have 2 bits and then add the 3rd bit. And this strategy is useful in a lot of problems. So let's think about it a little bit. So I have 3 bits, and I'm trying to add them. So I feed them to the first half adder, and one way of thinking about it is that first half adder is producing a 2-bit result. 1 bit at bit position 0 and a second bit at bit position 1 higher up. So if I were to start out by saying each one of these guys has a weight of 2 to the power 0, because they are in the same column, then when I subjected them to the half adder, then this guy represents bit at position 0, but this guy represents bit at position 1. Now, when I'm adding bits, I can only add them as bits if they have the same weight. So this guy had a weight of 2, the carry out of the half adder. This guy has a weight of 1. So I can add these two. Again, I have a half adder. Again, this guy will have a weight of 2 to the power 0 because same weight as input. This will have a weight of 1. And then here I kind of combine them together to get my carry out. So this circuit, you can kind of walk through it and convince yourself that it also implements the full adder. So in many ways we can implement the full adder. Now, perhaps the most important combinational module in our computers is the adder. Adder gets used for all sorts of things. And in fact, you'll see the same adder which we are discussing right now actually also works for signed numbers also. Okay, it can handle signed numbers also. Same adder. So there are highly optimized implementations of this full adder circuit. People have, back in 80s and 90s when there were early days of large-scale chips, VLSI circuits, people invested a lot of time on coming up with cool circuit tricks and all to optimize this. So now the question is, what shall we optimize? Going back out here, I have a, let's go back. Yeah, let's say here, full adder. So I have 3 inputs, A, B, and C in, and I have 2 outputs, C out and S. If you were tasked to make a fast adder, which delay would you optimize for? So I have 3 inputs, I have 2 outputs, A, B, C in, 2 outputs, C out and S. There are 6 possible delays out here, right? A delay from A to C out, B to C out, C into S, A to S, B to S, C into S, right? There are 6 possible ways I can go from input to output. Would you try to create a full adder where all the delays are the same, or would you try to focus on one of these, one or more of these 6 delays which exist? You want to answer? Which one? Everything which goes to the C out. Okay. Close, but not quite. So remember, how are we going to make our n-bit, 100-bit adder or 64-bit adder? I'm going to gang these things up. I'm going to start from, so my carry is going to flow through from bit 0 to bit 1 to bit 2 to bit 3 all the way to the end. I have to wait through all of that. So which delay matters then? Carry in to carry out. That's the most important delay. I can sacrifice on the other delays because this carry in to carry out delay is going to get multiplied n times, once for each bit. So the most important delay is therefore C in to C out. So let me go back to the circuit. This is the delay. This is a delay which we'll seek to optimize. This delay from here to here doesn't matter as much. With very small number of bits in an adder, of course it will matter. But we are talking about computers with 32-bit, 64-bit, 128-bit adders. So it's the other delay which dominates, and therefore you should focus on that. So in this particular case also, you would see that how the path from C in to C out is the one which is shorter, clearly it's going through fewer gates than the other way around. And people have gone through lots of transistor level hacking and all to kind of make that work out, because this almost always the adder is going to affect how fast the core CPU of your computer can run. Okay, so and then once we have a highly optimized full adder, then I can gang them up and create my n-bit full adder. Sorry, n-bit adder. So we'll have a half adder at the least significant bit and a bunch of full adders out there. Okay, so now I have a adder which can, which is pretty decent, but it takes linear time. I increase the number of bits 2 times, delay goes up 2 times. Can you think of some strategy which can help there? Could we make faster adders somehow? So let's say I were to ask you to add 10 bits. So one strategy is I can add bit number first 2 bits, take the result, add the third bit, take that result, add the fourth bit, take that result, and so on and so forth. In that case, my time will increase proportionate to n. Could you do better? Yeah.
If you can like do bits parallelly and then scale them together.
Yeah. So kind of like what we saw in arbiter also, which is you do a tree-like structure. You begin to add nearby bits, divide and conquer, okay, and keep track of their bit positions where they are, and then merge them. Okay. So if I'm adding, let's say if I'm adding, I had to add 4 bits. Okay. So bit 3, bit 2, bit 1, bit 0. So one way I could do it, I can say B0 plus B1, take its output, add to B2, take its output, add to B3. So now I have to do the 3 additions in sequence. Right? I have to first do the B0 plus B1, take its result, add it to B2, take its result, add to B3. But I could restructure the same thing as B0 plus B1, and in parallel, I do B2 plus B3, and then add the 2. So now I can have 2 adders working in parallel and then combine the result. So intuitively, I can play the same game with when I'm adding 2 numbers. Instead of always adding the lower bits, letting the carry ripple to the next one, and so on and so forth, I can start combining numbers, sort of upper part of the number and the lower part of the number, and then merge them together. So I kind of create a tree of adders, and these kind of adders are called carry look ahead adder and all, and they could be much faster because now we are driven by the depth of the tree. So instead of growing as linearly with n, they grow with log of n, log to the base 2, and therefore can be a lot faster. Like for example, if I'm adding 128-bit numbers, then instead of being 128 delays, it would be log 2 of 128, which is 7 gates of delay, a lot faster. So for big adders, you're probably not going to use this kind of what is called as a ripple carry adder. That's the name out here. This is called ripple carry adder. Because the carry kind of ripples through. Okay. So this is okay for small number of bits, but when you are adding very large numbers, then not a good idea. Let's explore another thing. So let's say I give you an 8-bit adder. an adder which can add 8-bit numbers. But I have two 16-bit numbers. We often face this thing in computers, right? I mean, I may be running on a 32-bit computer, but in my program, I may be using a long int. Long int in programming languages is usually either 64-bit or 128-bit. So while my computer only has a 32-bit adder, I'm adding larger integers. So let's go back to my example. I give you an 8-bit adder, but I give you two 16-bit numbers, and I ask you to add them. How would you do it? Okay, since it's almost the middle of the time, I hear the bells ringing. So let's take a 5-minute break and queue over this thing, and let's talk about how to. So again, two 16-bit numbers, but I only have an 8-bit adder. How will I add them? So 5-minute break. Let's
Yeah, I'm thinking about like, I think the truth is that I think I'm going to fall credit. Yeah.
Okay, let's start. So, anyone has any ideas? Would like to suggest something on how we can add two 16-bit numbers given only an 8-bit adder?
Just add the lower 8 bits of each number, and then hit the carry out, and then add that with the upper 8 bits of two numbers.
Good. So, I basically am kind of conceptually repeating the same process we were doing with the bits, except now we are doing groups of 8 and we are reusing the adder. Okay, so I need two steps. First step, we add the lower 8 bits, take the carry out, and then feed it as carry in next time around. So what that also suggests is that it would be good to have n-bit adders where at the bit 0 location also I can feed a carry in, so that I can do this kind of cascading multi-step adder. So instead of using a half adder, might as well use a full adder there. So this allows uh, doing larger adds. Okay, so I can play that kind of game out here. Okay, so now let's move on to, so we have seen adders. Of course, thus far, since we were only doing positive numbers, so we couldn't define subtraction because the result of subtraction could be a negative number. So we have to first figure out how we can represent negative numbers. We could have done multiplications. How do we do multiplications? So if, let's say I give you two numbers, x and y, I say, okay, add them. Multiply them. So the very first thing when we are taught multiplication is that, hey, repeated addition, right? I can keep adding again and again that many times, okay? So I can somehow kind of subtract one, but then we need to know how to subtract one from one of the multiplier, let's say, and do a repeated addition. So I can certainly do that. The other way we are taught long multiplication is to kind of make these partial products that we shift and then we add. So we have seen, again, in decimal world we have seen that, so we can do that as well. So we'll see those, but clearly sort of subtraction and therefore negative numbers are important. So let's talk about how we can represent negative numbers. So there are many ways one could imagine doing negative numbers. Not all of them would be mathematically clean, but I mean, I could have just picked some random mapping of those n minus the 2 to the power n patterns I have and then just give them some values, but it would drive us nuts to interpret them manually, and the side circuits may look rather horrible. So there have to be some clean structure to them. So there are three common ways that negative numbers are implemented historically. One of which is pretty much the dominant one, but you may encounter very well the other two also. So they go under the name of sign magnitude, ones complement, and twos complement. So let's see what they are. But so let's say I have the number 23. So at 23, I can represent, if all I wanted to represent was the number 23, then I could use 5 bits, and that would have been 10111. But of course, if I'm using all the 5 bits to represent positive numbers, I have a problem. I don't have any room left for negative numbers. So clearly, I need to have some additional bit. So, and roughly speaking, if positive and negative numbers are equally important, then when I'm trying to represent them, I would roughly like to have half the numbers in my bit patterns correspond to negative and half of them correspond to positive. So somewhat symmetric arrangement. So it would be kind of not a very useful system. So let's say I have 32 patterns available. I have a 5-bit pattern. Then I can go from -1 to 30, -2 to 29, -3 to 28. All these are valid ranges because they all correspond to 32 distinct entities. But not very useful. Probably more useful would be something like -16 to +15 or -15 to +16, something somewhat balanced. I commented last time that because of this 0, we cannot have a balanced representation because with k bits I have an even number of options and I need to represent 0, so I'm left with odd possibilities and therefore the range is always going to be asymmetric. Okay, either asymmetric or I need to have 2 representations for 0. So the way sign magnitude works is the following, as the name implies. I have the magnitude, which is positive, and then a separate sign bit. So 23 gets implemented as the magnitude of 23, which is 10111, and then a sign bit, and the convention is 0 is positive, 1 is negative. So 0 is 10111 is +23, and 10111 is -23. In each case, the magnitude part is the same. So this part and this part are the same. It's only the sign bits which differ. Whatever standard or system specification is would define how many bits you have for the magnitude. So let's say in this example, if instead of 5 bits of magnitude, I had 6 bits of magnitude, then +23 would have been 0, 0, 1, 0, 1, 1, 1. Okay, so the magnitude would have 6 bits. How would the 0 be represented here?
Will it be just like a positive number? Consider it to be a positive number?
So all zeros, or also 1 followed by the remaining 0, both 0 and -0, the same thing. So the problem with the scheme is that it has 2 representations of 0. And therefore, if my circuit produces either one of them, I have to somehow keep track that they actually the same value. So that's the ugly part. We could do what you are saying, which is we can say I'm only going to 0 will always be 0, 0, 0, 0, 0, and that we will never allow the pattern 1, 0, 0, 0, 0 to ever appear. That's not great either because I'm leaving 1 out of 2 to the power k option unused, so it's affecting my density with which I can store information, so it would be good to somehow use that also. But I could do that. So that's sign magnitude. One's complement. So what happens out in one's complement is, so the term one's complement, and actually in decimal there is a similar term called nines complement, and kind of the idea is that I am going to, whatever is my, so my positive number is the way it is, if it is positive number, it is the way it is in sign magnitude. Okay, so 0 followed by the magnitude. One's complement is that I subtract this thing out of all ones. Okay, which is another way of saying is I flip all the bits. Because remember, if I subtract it out of the number all ones, then 1 minus 1 becomes 0, and 1 minus 0 is 1. So I'm basically flipping the bits. So this number is obtained by subtract from all ones, or equivalently complement. As in negate. Take a knot, invert it. So if you look at it, this 101000, this guy, is obtained from 010111 by flipping each bit. So sign bit was 0 here, it becomes 1. Next bit was 1 here, it became a 0. Then it was 0, 111, it became 1000. So I complement it. In case of decimal, it's called similar thing is called nines complement, and it's basically saying subtract everything out of all nines, or replace each bit with 9 minus that, each digit with 9 minus all digits. So like 9's complement of 56 is 9 minus 5 is 4, 9 minus 6 is 3, so it's 43. So basically the complement and the original number should add up to the all nines, or in this case all ones. So this is one's complement. What's the highest positive number I can represent if I have a k bit ones complement number? So I have a k bit ones complement number. What's the highest positive number I can implement? 2 to the power k minus 1. No. 2 to the power k minus 1 would be all ones. Oh, to the power k minus 1. Okay. And then another minus 1. Because it has to be 0, 1, 1, 1, 1, 1. Okay, so it will be 2 to the power k minus 1 minus 1. Right? Because 2 to the power k minus 1 would be 1 followed by all zeros. Okay. Okay, so question?
Yeah, why do we have like the first bit? Because it seems to be it's redundant, because what are we going to need it like in the ones complement if we representing negative with ones complement?
No, but then if I didn't have that, then how? Let's say I didn't have it, then 0, 1, 0, 0, 0 is the number 8.
Oh.
Right? So I do need it. Okay? So I always need, the only way conceivably I can represent negative numbers is by having an extra bit. Right? So to represent the sign somehow. So the whole issue now is basically how do I organize it. Okay. So the largest in this particular case I have 6 bits. So the largest possible number, positive number, would have been 0, 1, 1, 1, 1, 1, which is 1 followed by 5 zeros, which is the number 32 minus 1. Okay, so anyway, so this is the same as 2 to the power, so I have 6 bits, so it's 2 to the power 6 minus 1, that's 32 minus 1. That's the value of this number. What's the most negative number? So most negative number would be the one which is a negative and its magnitude is the largest. Right? Okay, so now what's the most negative number? What in this case, the 6-bit case, what's the most negative number in just in terms of what the bits are?
The bits?
Yeah.
That's 1, 0, 0, 0.
1, 0, 0, 1 followed by all zeros, because its magnitude is all ones, which is the same as this. Okay, so the most negative number is minus because it would be 1 followed by what is the number 0? Anyone else wants to try? Yeah.
All zeros or all ones?
All zeros or all ones. Okay, so the number 0 in this case in one's complement is they both represent the same number 0. Okay. Again, so it This is another way, 1's complement. Turns out it has some nice properties, but it still has this ugliness of two representations of 0. So that led to what is called as 2's complement, and it is the pretty much all our computers use 2's complement. So because programming languages assume that we have 2's complement arithmetic, you will find 1's complement and sign magnitude only in more specialized situations. But if you have a general purpose computer capable of running C programs, Java program and all, it's going to be using 2's complement, because that's what, like I said, computer programming languages basically assume. Okay, so 2's complement, positive number is the same, 0, 1, 0, 1, 1, 1. Okay, but negative number is, take the 1's complement and add 1, take the 1's complement, think of the number as a positive binary number and add 1 to it. Okay, so what's happening is that, so again 0, 1, 0, 1, 1, 1, same as 1's complement. I take the 1's complement, so I get this, and then I add plus 1 to it, and then I get this. So let's see, so I got 1, 0, 1, 0, 0, 0, I add 1 to it, so I get a 1 out here, and the remaining bits are unchanged. So take 1's complement and add 1 to it. Or another way of saying is, so remember 1's complement was obtained by subtracting out of all 1's, right? If I'm taking 1's complement and adding 1 to it, that's another way of saying it, I'm subtracting out of all 1's plus 1, right? If 1's complement is subtracting out of all 1's, and if 2's complement I'm defining as take 1's complement and add 1 to the result, that's another way of saying that I am subtracting out of all 1's plus the number 1. What is all 1's plus the number 1? What would that look like? What's all 1's out here? It's right. I add 1 to it. What do I get? Anyone?
All zeros and overflow.
Overflow of 1. So I have a 1 at the, so it looks like this. So another way of saying is, or more generally now, it is going to be the number 2 to the power k, if I have k bits, right? So basically what we are doing is I take the magnitude of the number and subtract it out to the power k. So there are many different ways of looking at it, but this is called 2's complement. Now in this case, we do not, as we see shortly, we do not run into this problem of zeros having two representation. But what we give up in return is that this representation is not symmetric. There are fewer positive numbers, there are more negative numbers. There's one more negative number. It has to be that way because my overall choices are even. So if I am insisting that numbers have unique representation, then there has to be a non-equal number of positive and negative numbers. So why is 2's complement most important? It turns out, as we'll see, 2's complement makes subtraction really very easy. In fact, we just use our regular adder and it does subtraction also very easily. So as we just saw that if I want to represent a negative value, so if x is a magnitude and I want to represent negative x in 2's complement, then and I have an n-bit 2's complement number, then what really I'm doing is I'm doing 2 to the power n minus x. I'm getting that value, and then I'm saying what is the think of that as 2 to the power n minus x will be some positive binary number. I'll come up with its binary representation, and that is the 2's complement representation of minus x. So like for example, if I give you minus 6, then what you do is you look at 6 and then you do 2 to the power n minus 6, whatever is that value, and then you represent that in the bits that we have. Uh, the reason this works out, and again, bear with me for a short while, is that in effect, uh, uh, when we do additions on binary numbers or adder that we saw, if the overflow is discarded, then we are really doing a modulo addition. Anyone knows what modulo addition refers to? It's in high school curriculum, so recall. So when I say 2 plus 3 mod 4, what is that? Anyone? Yeah.
So if you take those numbers in 1, 4, for example, 2 would be 2 and 4, and 3 would be 1 and 4.
Right. So
And you add them up.
you add them up and you take the remainder. Okay? So our adder, if you recall, what was happening was if my two numbers were adding to something very big, then I was getting a 1 in the overflow. If I ignore that, then the remaining part is the remainder left over. So my n-bit adder is actually doing a modulo to n, modulo to the power n addition, if I ignore the most significant bit. So there is a rollover effect, basically. So if I take the number, sticking to positive binary numbers, let's say I have a 5-bit adder, or let's keep it simple, 4-bit adder. If I take the 4-bit unsigned binary number 1111, that's the number 15. I add 1 to it. I will get 1 followed by 4 zeros, but I'm discarding the 1, so I really have all zeros. So I'm getting a 0. And that makes sense because if I had the number 15, 15 plus 1 is 16. 16 modulo 16 is 0. So I should get back a 0. So an n-bit adder, n-bit adder, when we are doing positive binary numbers, is really doing mod it's doing a modulo 2 n bits addition. And that property ends up playing a useful role. So let's see how it plays a useful role. So again, let's limit ourselves to 4 bits. 4-bit 2's complement numbers now. Okay? So let's see what would happen. So if I have 4-bit 2's complement number, what's the largest positive number I can represent? Seven. You just give me the bit pattern. So 0, 1, 1, 1. Right? 0, 1, 1, 1, which happens to be 7. Okay. What is the representation of 0? All zeros. What do you think is this number? Negative 1. And that kind of follows that if I have a negative number in 2's complement, you take its 2's complement and you will get back the magnitude. So it would be 2's complement of this would be take the 1's complement, that's all 0, add 1 to it, find it 1. And then finally, what do you think is this number? Negative 8. Good. So, and if you think about it, normally we think of numbers as 0, 0, 0, 0, 0, 1, 0, 1, 1, and then after 0, 1, 1 comes 1, 0, 0, right? But what we have done is we have kind of taken all those numbers which have most significant bit as 1, we have moved them to the negative side. So there is kind of a wraparound happening out here. So when I only had unsigned numbers, then I went from 0, 0, 0, 0 all the way to 1, 1, 1, 1. So somewhere along the way, I would have gone to 0, 1, 1, 1, then I would have gone to 1, 0, 0, 0 if I ordered them. In 2's complement, I took that upper part and shifted them to the negative zone. So let's see a bit more. So what this in turn leads to is the following, that if I have 2's complement representation and I want to add them or add the two numbers, which now may be negative, okay, because they are 2's complement numbers, I can just use my regular good old adder. And the reason it works is the following. Let's say I have a positive number x and I have a negative number minus y being the magnitude. And we saw that negative y, I'm going to be representing it as 2's complement. So it has the same bit pattern as 2 to the power n minus y. That's how the 2's complement itself was working, right? 2's complement was 1's complement plus 1, and therefore it's the same as subtracting the magnitude out of 2 to the power n. Further, so this is the bit pattern of this guy is going to be that, then this is the bit pattern. And furthermore, we know that our binary adder, as we just saw, adds modulo 2n. It ignores the overflow. So all this, so this bit pattern and this pattern, when we add and ignore the upper, do a modulo 2n, what will this look like? X plus 2 to the power n minus y modulo 2 to the power n. That's the same as x minus y, because 2 to the power n will disappear in the division. So this thing is going to be the, well, let me go back. As a result, this thing is, well, we all same as x minus y, which is what we wanted, x plus the negative number y. So two things are coming together out here. One is that taking 2's complement, if I want to find 2's complement representation of a number whose magnitude is y, then what I do is I subtract y from 2 to the power n. That will give me some positive number. And I think of my k bits that I have as representing that positive number. And whatever that bit pattern is the bit pattern I would have obtained by 2's complement. So that's property number one. And property number two is that our adders, if we ignore the overflow bit, are doing modulo 2 to the power n addition. They have this rollover effect. And as this little equation shows, I would get the right result. X plus the number minus y, where y is a positive magnitude, is the same as adding x plus whatever is the bit pattern for 2 to the power n minus y, and I'm doing all of that modulo to the power n. If I'm doing modulo to the power n, that term inside 2 to the power n will disappear, and therefore I will be left with x minus y, which is what I want. So this little proof kind of says that, look, the nice thing out here is my very same binary adder, which was working for when my bit patterns represented positive or whatever unsigned binary numbers, also works for 2's complement thing. It does x plus, whether I take two numbers, whether they are positive or negative, they are still going to work. I may have overflow. If I take two positive numbers in 2's complement which are too big, like in our example, let's say I have 4-bit numbers. So let's say I were to add, this is the number 6, and let's say this is 0, 0, 1, 0. This is the number 2. 6 plus 2 is 8. 8 cannot be represented in 4 bits because the highest positive number is 8. Highest positive number is 7. So what will happen out here? There will be an overflow that will happen. So let's add this. I'm going to use, so even though these are 2's complement, I'm going to just use our regular adder. I'm going to think of these bit patterns as if they were positive numbers, just regular unsigned numbers. I'm going to add them together. So 0 plus 0 is 0, 1 plus 1 is 0, with a carry of 1, 1 plus 1, 0, carry of 1. That's what I get, 1, 0, 0, 0. But I now have an overflow because this number is minus 8, not plus 8. Because now I'm going to change hat. So I started out with 6 and 2. Then I said, hey, let's think of them as positive binary numbers, the bit patterns themselves. Add them using my adder. And then whatever bit pattern I'm getting back, now let's think of it as a 2's complement number. So what's happening is I get 1, 0, 0, 0, which is minus 8. There is an overflow. Or more, there is an overflow. And so instead of getting an 8, which could not be represented, I get a minus 8. What do you think if I were to add two very negative numbers? So let's say I were to add, what's minus 6 in 2's complement? Someone help me. Minus 6, what's the bit pattern for minus 6 in 2's complement? 1, 0, 1, 0. And what's the bit pattern for, let's say, minus 3? Hmm? 1, 1, 0, 1. 1, 1, 0, 1. Yeah. That's minus 3. If I add them together, I should get minus 9. But we know minus 9 cannot be represented. So something weird is going to happen in this case. So first thing is I'm going to again think of 1, 0, 1, 0 and 1, 1, 0, 1 as if they were representing positive unsigned binary numbers. I'm going to add them using my regular adder. So 0 plus 1 is 1, 1 plus 1 is 1, 0 plus 1 is 1, and then I get a 0, and there is a carry out, which I ignore. So I get 0, 1, 1, 1, 1, and that's a 7. That's a positive 7 in 2's complement. So again, obviously something, it's going to give bogus results. Do you see a pattern out here? So that how can you detect? So in this case, I have what is called as an underflow. I have too small a number. So this was overflow. This is underflow. Sorry about it. Okay. Do you see some pattern out here? What happened in case of when I tried to add two very positive numbers? So temporarily we are interpreting, so my two positive numbers, temporarily I said, hey, let's think of them as n-bit unsigned numbers. So when I add them, they will go further up the number line. And in particular, what happened to the first bit? It became 1. So I started by adding two positive numbers, but I ended up with a negative number because these numbers were very positive, and therefore when I added them, they moved further up in the positive territory when viewed as unsigned numbers. So their most significant bit became 1, but that actually is the negative territory when I think of the same bit pattern as negative numbers, as 2's complement numbers. And exactly the opposite happened in the negative case. I had two negative numbers, which when I added them would have yielded an even more negative number, but that would have wrapped around and gone back to positive territory, and therefore I see a 0 at the first. So if I start with two positive numbers and the result is negative, something weird went on. If I start with two negative numbers and the result is positive, something weird went on. If I have a positive number and a negative number and I add them, how many of you think an overflow can happen or an underflow can happen? So I take, in our example, 4-bit numbers. I take two 4-bit numbers, one of which is, when interpreted as 2's complement, one is positive or the other is negative. If I add them together, do you think can we ever have an overflow or an underflow? And why not?
Because the left is 0 and 1, so if you get over, carry 1, so.
Well, okay, so let's think about it just purely numerically, right? If I have a positive number and I'm adding a negative number to it, then I can only end up with either a smaller positive number, in which case I'm okay, or I can go into negative territory, but my negative number can never be so big as to take me all the way past the negative territory also, because I was starting out in the positive territory. So whatever number I end up with is going to be either a smaller positive number or something which is a valid negative number. And likewise, you can think of that way. So this is more example. Let's say I'm trying to do 4 minus 3, or which is really saying 4 plus minus 3. Minus 3 in 2's complement would really have the value 16 minus 3 when viewed as when its bit pattern is viewed as a unsigned number. So 4, what's the bit pattern of 4? It's 0, 1, 0, 0. That's 4. And bit pattern of minus 3 is 0, 0, 1, 1. Take the 1's complement, it's 1, 1, 0, 0, and it's 1, 1, 0, 1. So that's the bit pattern of minus 3. And 1, 1, 0, 1, when thought of as a positive binary, unsigned binary number, what is its value? 8 plus 4 plus 1, 13, which is 16 minus 3, which kind of makes sense. So see how back and forth I'm going between looking at the same 4 bits as a 2's complement number, and then the next moment I'm saying, hey, let's think of it as a unsigned binary number. And that's the trick that's going on out here, that 1101 is minus 3 in 2's complement, but when viewed as a regular unsigned binary number, it is 13. So on the right hand side, what's happening is we started out with sort of 2's complement, but we said, hey, let's think of these bit patterns as regular binary number. We are going to use a regular binary adder, which does this modulo to the power n behavior. So I have 4 plus 16 minus 3, mod 16, which becomes 4 plus 15 minus 3, blah, blah, blah. We end up with 0, 0, 0, 1, which is what we would expect. Okay? So things sort of work out as a consequence of this behavior. So again, 2's complement, because of this very interesting property that 2's complement can be viewed as 2 to the power n minus x and negative numbers, and that our adders do modulo 2 to the power n arithmetic. All of that translates into that our standard adder works as an adder for 2's complement also. I don't need to create a special adder. Whereas with sign magnitude and 1's complement, I would need a more complicated adder circuit. If nothing else, because those systems have 2 representations for 0. So I would need to have some sort of a complicated way to handle them. Here, I don't need to do anything special. The adder we already saw earlier today is the adder which works out nicely. So that's the most important property. This I have already shown that normally So if you think of our binary numbers, 4-bit binary numbers, as kind of forming a wheel, 0, 0, 0, 1, 1, 1, and we reach 1, 1, 1, and we normally when we think of them as standard positive binary numbers, I think of them as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 30. But instead of that, we have reinterpreted those patterns in a particular manner so that 1, 1, 1, 1 is -1 and so forth. Okay, so we go from -8 through 7 to do this. And so it's the same wheel, but we have reinterpreted it, and this is what allows us to go back and forth very easily. We don't, every number has a unique, every bit pattern has a unique 2's complement interpretation, whereas we could not say the same thing in case of 1's complement and sign magnitude. So we are at the end of the lecture time slot. We're going to pick up this thread again. 2's complement is something I want you to be intimately comfortable with. You should be able to kind of do these additions and all in the text.